Now, another flashback I talked about earlier, but I want to talk about again. You can find the system enthalpy for a reaction if you have a table of enthalpy values. And you take the sum, which is what that symbol is right there. You take the sum of all the enthalpies of the products, and you subtract from it the sum, which is that symbol right there too, of all the enthalpies that are reactants. And if this is totally like blah, 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 and you can't get your mind around it, well, let's do an example. It's not a hard process. You do need a table of enthalpy values to make this happen, but here's how this works. So let's say we want to find the enthalpy of this reaction, which is 2 hydrogens and an oxygen making 2 waters. Okay, we're going to need the enthalpy values for liquid water. We're going to need the enthalpy values for both hydrogen and oxygen. And if you remember from this stuff back in Chem 221, Chapter 5, and if you don't, I do recommend you look in Chem 221, Chapter 5, just to make sure you're up to speed with it. Some of those species have enthalpies of 0. And all of the elements in their standard states have enthalpy values of 0. So the overall way to find the delta H, products minus reactants. This part right here, that's the products. We have 2 liquid waters. And then there's a minus, and then the part in square brackets here, that's the enthalpy of the reactants. So products minus reactants. Now, the number that's right there, that's the value when you look it up for water as a liquid, okay? If you look up hydrogen and oxygen, they have values of 0. And notice that because of the stoichiometry, we're going to multiply the water by 2. If hydrogen had a value, we'd multiply it by 2. Oxygen, though, we just multiply by 1 because that's the stoichiometry of it. If you look this all up in your book and you do the problem right, and I encourage you to do it, you should get a delta H for this reaction minus 571.70 kilojoules per mole. And just as some quick reminders, all right, the pure elements have values of delta H equal to 0. These are heats of formation, all right? We look the values of delta H up in the table, and there's one in problem set 5 to use. This is an exothermic reaction because delta H is a negative number. If it was a positive number, we'd call it endothermic. And again, that little 0 there just means standard conditions, 298 Kelvin, 1 atmosphere of pressure, etc., etc. So that's kind of a quick flashback to Chem 221. We're going to do something very similar here. In this case, it was delta H equals delta H products minus delta H reactants. We're going to do similar things with other thermodynamic quantities here in just a little bit. For example, you can calculate the change in entropy for a reaction just like you did the change of entropy and change of enthalpy for a reaction. And you can see the problem here. It looks very similar to what we just did. If you want to find the delta H of a reaction, say this reaction we looked at earlier, it's all the delta S's of the products minus all of the delta S's or the S values for the reactants. So just like before, we need to look up the values, products minus reactants. We'll have 2 liquid water values minus the 2 hydrogens and the oxygen. Now, in entropy, remember the only time you have 0 entropy is for the pure crystal at 0 Kelvin, which is like never. So what that means is that unlike enthalpy, we do need to look up values for liquid water, for hydrogen gas, and for oxygen gas. So if you do this, all right, the overall delta S, it's products, which is that part right there, minus this part right here, which is the reactants. So products minus reactants, and the stoichiometries follow. So we're going to multiply the liquid water by 2. We're going to multiply the other ones by whatever they need to. And unlike enthalpy, H2 and O2 have entropy values. You need to look them up, okay? So when you do this, 2 moles of product minus the 2 hydrogens plus 1 mole of oxygen, you get a delta S of the system, which we'll talk about in a little bit here, negative 326.9 joules per Kelvin, All right. So what this says is there's a decrease in entropy for this reaction. And if you think about why that's the case, you can see why too. We have 3 moles of gas going to 2 moles of liquid. So first of all, entropy is always higher for gases than it is liquids. So turning gases into liquids, entropy doesn't like it. All right. Also, we have 3 moles going to 2 moles, and 3 moles of reactant is more disorder than the 2 moles of product. So the matter is becoming more concentrated. Entropy really doesn't like this reaction because you have gases going to liquids and 3 moles going to 2 moles. Nothing about this is making entropy very happy. Let's calculate the standard entropy change for this reaction. This is copper metal reacting with half of an oxygen gas to make copper 2 oxide, CuO. And again, the process we want to use, entropy of products minus entropy of reactants. So you can see the different values right there. All of them are positive numbers initially because the only time you'll have 0 is those pure crystals at 0 Kelvin, which is never, and also individual entropy values will never be negative. So anyway, we take the copper oxide, which is this number, and subtract just the copper and 1/2 the oxygen. So do this in your calculator or just see what happens here in a little bit. The entropy here, copper oxide minus the copper and half an oxygen, you end up with a negative 93.12 joules per Kelvin value. So entropy is decreasing in this reaction. And again, because a gas is being formed into a solid, and because you have 1.5 moles going to 1 mole, all of those things make entropy not like this reaction and give it a negative number. If entropy gets a positive number, an overall positive delta S, then entropy is happy, an increase in entropy, etc., etc. Another thing that we need to talk about here real fast before we get into the gist of this chapter is calculating an entropy of formation. And that little f right there is something that's really important for scientists. The table of thermodynamic values, which is at the end of problem set 5, is basically a list of formation values for enthalpy and for entropy. And in Chem 221, we talked about the enthalpy of formation, and that's when it gets a little f right there. And it can be a formation enthalpy if, and only if, you have 1 and 1 only mole of product. And the other thing is that you have to have reactants as elements in their standard states. So you can only have an entropy of formation, or an enthalpy of formation for that matter, if 1 mole of product and reactants are elements in their standard states. So this reaction right here, where hydrogen and oxygen are making liquid water, that is a formation reaction. And if we want to define the entropy of formation from it, this would be a good candidate because we have 1 mole of product, 1 mole of liquid water, and all of our reactants are elements in their standard states. So we can calculate those values. We'll look up in the same tables that we did before. We'll take the products, which is 69.9, the water value, and we'll subtract the reactants, which is 1 hydrogen and half of an oxygen, and we end up with an entropy of formation, negative 163.5 joules per Kelvin. So this is how you find the entropy of formation. You can also do the similar kind of thing to find an enthalpy of formation, but the difference with enthalpy of formation is that all of the reactants had values of 0. In enthalpy, H2 and O2 gas would both have values of 0, but with entropy, you actually have to calculate what those numbers are. So if you have the entropy of formation values, that's awesome, but if you don't, you can calculate them using this system right here. Which of the following is the reaction for an entropy of formation? Now remember that to have an entropy of formation, or any formation for that matter, you can have 1 mole and 1 mole only of products, and all of the reactants must be elements in their standard states. So if you look at the first one there, making manganese 2 hydroxide, well, we do have 1 mole of product. That's cool. However, hydroxide nor manganese 2 plus are reactants as elements in their standard states. It's not manganese metal and oxygen gas and hydrogen gas, which would be the elemental versions. So A is not a formation reaction. B, you can see there's lots of products, and you can only have 1 mole of product in a formation reaction. B would be a formation if it was reversed, if you had KClO3 as the product and all of those pieces there were the reactants, but it's not, so that's the way it goes. Now, C has 1 mole of product, all right, which is cool, but it doesn't have, again, elements as standard states for reactants. CaO and CO2 are both compounds. Those aren't elements in their standard states, so that one doesn't fly either. But answer D, if you look at that, we have 1 mole NaOH, we have 1 Na, elemental sodium, we need 1/2 of oxygen and 1/2 of hydrogen, and those are elemental states. Well, guess what? Answer D is a formation reaction. And I bring this one up because I hate using fractions when it comes to balancing reactions. But in a formation, whether it's enthalpy in Chem 221 or entropy now, you sometimes have to use fractions. And I don't necessarily like it, but even I, with my PhD, I have to use fractions when it comes to formation reactions. Answer E is not a formation either, because you have 8 moles of product. You can only have 1 mole of product, etc., etc. We talked about the first law of thermodynamics. First law says energy can't be created or destroyed. We talked about the third law of thermodynamics, where the only time you're going to have 0 entropy is for that perfect crystal of an element at 0 Kelvin, which is basically never. The only one left to talk about then is the second law of thermodynamics, and this one is huge. It may not look that way at first, but trust me, this one's going to rock our world. Second law states that a reaction is only spontaneous, i.e. product favored, if the delta S for the universe is positive. Now, if you're talking about delta S of the universe, you have to realize the universe has a system and a surroundings, all right? The chemical system, in our case, we're looking at, and everything else around it. If you're going to have a spontaneous product-favored reaction, you must have an increase to the entropy of the universe, to the disorder of the universe. That's when you're going to have spontaneous product-favored, usually irreversible processes. So if we want to calculate the entropy of the universe, we have to first of all calculate the entropy of the system. And the entropy of the system is usually what we do when we calculate matter dispersal. And that's like classic entropy, all right? Because classic entropy talks about moles being dispersed and liquids versus gases, et cetera, et cetera. But we also then need to think about the entropy that's created through energy dispersal. And that's going to be the delta S of the surroundings. So if we can calculate the delta S of the system and the delta S of the surroundings, we can add them together. And if the delta S of the universe is greater than 0, that means its reaction's going to occur. It's going to be product favored. And on the other hand, if delta S is less than 0, then the reaction won't be product favored. It'll be reactant favored, not as likely to occur. If you're kind of underwhelmed by my description so far as to why this is important, trust me, I understand. But here's the thing. Let's say that someone said, hey, how would you like the magic power to predict if a reaction was going to occur? I mean, any reaction, any chemicals, blah, blah, blah. Well, you'd probably say, score. Absolutely, I want that. Superpower. But anyway, all right, superpower maybe is an exaggeration, but hopefully you get the idea. This law is actually the equivalent in a chemistry term for that kind of superpower. Because if you can calculate the delta S of the universe, and if you find it's greater than 0, that reaction is going to occur. And it can be any combination of chemicals, any conditions, blah, blah, blah. So this is why scientists want to do it. They want to know if sodium chloride reacts with silver nitrate, all right? Or if potassium hydroxide reacts with hydrochloric acid. Those are the kind of questions that scientists would love to be able to tell, and this is their key to finding that out.
When we dissolve ammonium nitrate in water, The dissolution is an endothermic process. The temperature of the solution decreases over the course of the reaction. The reaction, though not favored energetically, is favored by entropy. It is said to be entropy-driven. As the ammonium nitrate dissolves, the entropy of the system increases. At the same time, the surroundings lose energy and experience a decrease in entropy. The increase in system entropy, however, is greater than the decrease in the surroundings entropy. Thus, the total entropy, the sum of the entropy changes in the system and surroundings, increases as demanded by the second law of thermodynamics.
We're going to go back to the example of ammonium nitrate dissolving in water. Woohoo! Not very exciting, but remember, it is kind of exciting scientifically because it's an endothermic process. The temperature is going down. On the other hand, it is spontaneous, all right? The reaction is occurring. So, using the second law of thermodynamics, delta S of the universe equals delta S system plus delta S surroundings. Well, overall, delta S of the universe must be greater than 0, okay? So the question is then, what's happening here? Delta S system, delta S of the surroundings. Well, the surroundings is related to the temperature. It's pulling energy from the outside in, all right? So if energy is being pulled from the outside to the inside, entropy of the surroundings is not a positive number. On the other hand, ammonium nitrate, that nice ionic lattice solid being dissolved into liquid water, breaking up into ammoniums and nitrates and stuff like that, that must have a delta S system value that's greater than 0 because something is making delta S in the universe greater than 0. So if the matter distribution is overpowering the endothermic value of the delta S of the surroundings, that's what's going to make this reaction occur. It's going to make it spontaneous. Let's go back and look at this reaction real fast. We're going to calculate the delta S of the universe for hydrogen and oxygen making liquid water. And earlier in examples, we did both the entropy calculation, which is delta S of the system, by the way, and we also did the delta H calculation, which is going to be related to delta S of the surroundings. If you go back in your notes, the delta S of the system, which was the products minus reactants thing we did earlier, came out to be negative 326.9 joules per Kelvin, all right? And we talked about how that's entropy disfavored, i.e. negative number, because 3 moles of gas are going to 2 moles of liquid, etc., etc. Delta S of the surroundings from other classes you will find is equal to the Q of the surroundings divided by the temperature at which it occurs. And the Q of the surroundings is equal to the negative of the delta H of the system. So what that means for us here is that delta S of the surroundings equals negative delta H of the system divided by the temperature. Now, the delta H of the system is actually a number we already calculated. That was the delta H of products minus delta H of reactants. And we saw that the hydrogen and the oxygen had 0 values, but water was a number we could look up. We ended up calculating it was a negative 571.70. So we're going to take this delta H of the system and we're going to calculate the delta S of the surroundings. And we've already got delta S of the system, so you can probably see where this is going. First of all, let's do the delta S of the surroundings. So negative of the delta H is negative, negative becomes a positive. We'll turn the kilojoules part of delta H into joules. We'll divide it by the temperature at which it occurs, and these are all standard conditions, so 298. Delta S of the surroundings, positive 1917.5. We've got a 1917.5 delta S of the surroundings. We have a negative 326.9 delta S of the system. So we've got all the pieces now that we need to calculate the delta S of the universe for this reaction. And again, on that last slide, delta S of the system, negative 326.9 joules per Kelvin. Delta S of the surroundings, positive 1917.5 joules per Kelvin. Make sure that you translate, by the way, delta H, which is usually in kilojoules, to a joules per Kelvin if you're doing this process. But anyway, second law of thermodynamics says that delta S of the universe equals delta delta S of the system plus delta S of the surroundings. So if you add those two pieces together, positive 1590.6 joules per Kelvin. And this is a positive delta S of the universe value. So that means this reaction is product favored. And to be honest, thank the stars it is, because this is the formation of liquid water. And liquid water, which is very abundant on the Earth, thankfully, forms pretty readily. Now, the delta S of the system number right there implies that maybe it wouldn't, because the delta S of the system, 3 moles of gas going to 2 moles of liquid, entropy here is not very happy. But fortunately, the delta S of the surroundings is so positive, it overwhelms the delta S of the system, giving an overall positive delta S value. So we hope that water forms. It does. It has a positive delta S. Woohoo! You just used a superpower. You found out that this reaction is spontaneous. It's going to happen. It's product favored. So that's good. Water forming from the elements does occur. And that's what's kind of cool about all this.
A balloon filled with hydrogen and surrounded by air represents a potential chemical reaction. To initiate the reaction, we need to ignite the balloon. The hydrogen will combine with oxygen in the air to form water in gaseous form, releasing considerable energy in the process. At the molecular scale, the molecules of gaseous hydrogen, H2, and oxygen, O2, combine to produce H2O, water, generating heat and light. In the combustion of hydrogen and oxygen, the entropy of the atoms in the sample, or system, decreases. This decrease occurs in concert with the transfer of thermal energy to the surroundings, leading to an increase in the entropy of the surroundings. The entropy increase for the surroundings is greater than the decrease for the sample, so the net change in entropy is upward.
So it's kind of interesting, like the hydrogen and oxygen by itself, the entropy of the system was totally fine with it, like don't change, all right? On the other hand, once the hydrogen and oxygen were allowed to react to make water, lots of energy was released. So even though you end up with fewer moles, and fewer moles of liquid, by the way, which is all entropy disfavored, the overall energy is distributed really well through the outside. So the container would feel warm, or other molecules would rotate, vibrate, move around faster, that kind of stuff. This is how you can think about these reactions. And if you compare again the system entropy to the surroundings entropy, you can actually figure out if a reaction is going to be product favored or not. So this reaction with a positive delta S would be very product favored. We expect water to form. Which of these reactions would you expect to have the largest positive entropy change? Okay, really good question. Now, the first one is 2 molecules of gas going to 2 molecules of gas, all right? Probably not going to be a big entropy change there. You could argue that maybe you're getting more ordered because you're going to individual I2 and F2 instead of the mixture right there. But we would not expect to necessarily have a very big positive energy change. It might even be negative. Honestly, I don't know. But I'm not excited by it, as you can probably tell. All right. Now, B, gas going to liquid, we would absolutely disqualify that because gases have more entropy than liquids. Gases going to liquids would not have a positive entropy change. Let's skip to D real fast. A liquid going to solid would be equivalent because, again, solids have less entropy than liquids, so that would probably not be favored. But let's look at C now. Now, C is an example of a combustion reaction, which is something we talked about in Chem 221, where you take something organic. This is benzene, C6H6, by the way. It reacts with oxygen. It's got a fraction there. I know. I'm going to get over it. Anyway, it makes CO2 and some water. Okay, now this one I think is going to have a big entropy change for 2 reasons, all right? The first reason is that if you look at the moles of gas, all right, 15 over half, 16 over half would be 8. So you have like 7.5 moles of oxygen plus 1 mole of liquid. That would be 8.5 moles on the reactant side. And those 8.5 moles are going to 9 moles total. So fewer moles going to lots of moles. That's making the entropy of the system actually happy, more disorder. Also notice that one of the moles on the reactant side is a liquid. Everything on the product side is a gas. So if you can go liquid to gas, that's a pretty good indication that's going to be entropy favored. But the other thing is that because it's a combustion reaction, those reactions are super exothermic. They burn easy. So that reaction is going to have a good delta S of the surroundings as well. Because if you burn something, energy is released. It goes into the outside. So for both system and surrounding values, I would argue that C is the best answer. 8.5 moles going to 9 moles is definitely good. A mole of liquid turning into gas, also good. Combustion reactions make the delta S surroundings going to increase as well. Very cool. Also notice there what I did for delta S of the surroundings. I used an enthalpy term, an exothermic reaction, which is what a combustion reaction is, to justify why delta S of the surroundings would be positive. That's where that delta S of the surroundings equals negative delta H over T part comes in. But you can also see how we're going to come back to enthalpy here in a little bit. Enthalpy is a little easier to use usually in chemistry than the delta S of the surroundings. So here are several combinations that talk about if you have a spontaneous process or not in terms of delta S of the universe, all right? Now, delta H is proportional to negative delta S, or negative delta H is proportional to S of the surroundings, all right? And you can see there's 4 possibilities, and they all involve essentially enthalpy versus entropy. Now, what's confusing about using the delta S of the universe is that you have to convert delta H to the opposite for delta S of the surroundings, but it can be done. I also want you to see that there are 4 possibilities. In one way, the enthalpy and the entropy are working together to make the reaction spontaneous all the time, which would be delta S of the universe greater than 0. You also have a condition of delta H and delta S, which are working together, but to prevent a reaction from going. And there are some reactions which won't be spontaneous like ever. And then there's 2 conditions in the middle where either entropy or enthalpy want the reaction to go, but the other one doesn't. And there will be a temperature dependence on that. We're going to talk more about this, but in a different context here coming up. But these 4 possibilities to explain if a reaction is going to occur or not can be really helpful. And we'll look at this in a little bit different light in just a little bit. Gibbs looked at the delta S universe equation and thought, well, that's nice, but as a chemist, we use delta H all the time. So instead of using delta S of the surroundings, he put in negative delta H system over T. And the advantage there is that delta H of the system, that's the delta H of products minus delta H of reactants. And chemists have always been really good about that. But obviously, this equation right now is kind of ugly. All right, negative delta H over T plus delta S, pretty funky. So he multiplied everything through by negative T. And when he did that, he got negative T times delta S of the universe equals delta H of the system by itself minus T delta S. And that looked a little bit better. But what people realized is that negative T times delta S of the universe, you can actually think about it as its own thermodynamic quality. And so what people did eventually is negative T delta S of the universe equals another thermodynamic quality called delta G of the system. And delta G is what they refer to as Gibbs free energy. And Gibbs free energy is yet another thermodynamic quality. So there's delta H enthalpy, there's delta S entropy, now there's delta G Gibbs free energy. So if you have standard conditions, delta G equals delta H minus T delta S. This is the Gibbs free energy equation. There's a picture of good old Gibbs up there. Now, at this point, you're probably like, yeah, that's a lot easier. What are you talking about? Well, okay, here's the chemist's perspective. It's easy to calculate the delta H of a reaction, delta H products minus delta H reactants. It's also easy to find the delta S of a reaction. We saw that already, delta S products minus delta S reactants. You've got a table, you'll have delta H and delta S values. Well, if you know the temperature, then you can quickly calculate the delta G value. And delta G is related to negative T delta S. So if delta S of the universe is positive because of the negative T, that means delta G is going to be negative. And if delta S of the universe is negative, negative T times negative means delta G is going to be positive. So you can relate delta G back to the spontaneity. And in chemistry, that's what people do. They're always talking about delta G values and how it relates to spontaneity. But in your own mind, just realize that delta G really comes from negative T times delta S of the universe. And this is all related to second law and stuff like that. Oh, joy. Delta G equals delta H minus T delta S is arguably the most important equation of all of chemistry because we're going to use this delta G to see if a reaction occurs or not, if it's spontaneous or not, all right? And the Gibbs free energy is just literally the energy change for the system minus the energy lost in disordering the system. So delta H now, that is the energy change for the system, and the delta S is the energy lost in disordering the system. Remember, delta S is just a measure of messiness. If you have an exothermic reaction with a negative delta H, and you have an increase in the entropy, which is a positive delta S, look what happens. You have a negative delta H minus a positive delta S. Delta H is negative, delta T minus T delta S is negative. You're always going to have a negative delta G. So if you want a reaction to be spontaneous all the time and product favored, you want a negative delta G. And you will always get a negative delta G, a spontaneous reaction, if you have an exothermic reaction and an increase in the entropy, a negative delta H and a positive delta S. Those conditions with negative exothermic enthalpies and positive increases of entropy will always be spontaneous, always product favored. But we don't always have that because sometimes you'll have, for example, an endothermic enthalpy, which would be a positive delta H, and you'll also have a decrease in the entropy, and that can be a negative delta S. We've seen a couple of those. Well, if delta H is positive, delta S is negative, but negative times negative makes it positive. In those cases, delta G will always be a positive number. So if you end up with a reaction that's endothermic and a decreasing entropy, you will always be in a non-spontaneous state. Those reactions just won't occur. They're going to be reactant favored, or they won't occur to a very appreciable extent like we've seen with equilibrium and stuff like that. So if you want your reaction to go, you want it to be exothermic with a positive delta S. On the other hand, if you do want a reaction not to occur, and there are cases of that, you want a positive delta H and a negative delta S because those conditions will always give you a positive delta G. So delta G, when it's negative, spontaneity will happen, product favored. But if delta G is positive, you'll have a non-spontaneous reactant favored condition, and those won't be likely to occur. Let's calculate the Gibbs free energy change for this reaction. And there's delta H and there's delta S. So to do this, delta G, which is what we're after, equals delta H minus T delta S. Couple of things. Make sure your temperatures are in Kelvin. All right, very important in thermodynamics. And second of all, notice that the units there, delta H is often kilojoules and delta S is often joules. So make sure you convert one to the other. Because our answers here are all in kilojoules, I would recommend turning your delta S into kilojoules first before multiplying by the Kelvin temperature. But anyway, plug and chug, delta G equals delta H, and you can see I just used the value as is, minus T, so 25 Celsius is 298 Kelvin, and then the delta S value, which is negative, I turned it into kilojoules. So I divided by 1,000. It became minus 0.10836. Anyway, the number came out to be a negative 568.9. Negative delta G's are spontaneous. So this reaction is going to occur at room temperature, which is pretty cool. The negative sign of delta G tells you the reaction's good to go. If this would have been a positive delta G, we would have said it was non-spontaneous. Non-spontaneous reactions don't occur by themselves. There are 4 conditions of delta H and delta S that are possible, and scientists like to think about this because it affects the sign of delta G. So we talked about earlier how if you have an exothermic reaction and an increase in the entropy, the delta G is always negative. Those are always going to be product favored, spontaneous. Those are going to be good to go. On the other hand, if you have an endothermic delta H and a decrease in the entropy, a negative delta S, then your delta G in those cases will always be positive. And positive delta Gs are the reactant favored non-spontaneous reactions, and those are hard to do. There's 2 more possibilities though. The first possibility down here is when you have an exothermic reaction but a decrease in the entropy. Now in this set, the delta H exothermic, it wants the reaction to go. A negative delta H contributes to a negative delta G. On the other hand, delta S is negative. Delta S says, I don't want this reaction to go. I'm not happy with it. So here, enthalpy and entropy are fighting, all right? Enthalpy wants the reaction to go. Entropy doesn't want the reaction to go. In these cases, then, it really depends on your temperature. Temperature times delta S can overpower delta H. If your temperatures are high enough, then temperature times that negative delta S makes for a positive number. Positive numbers don't contribute to negative delta G's. So in this case, you would say that high temperatures make the reaction non-spontaneous and low temperatures make this reaction spontaneous. On the other hand, the last set there, it's the opposite. Now we have an endothermic delta H. Endothermic reactions don't really wish the reaction to be spontaneous, but you do have an increase in the entropy. So entropy wants the reaction to go. If entropy times temperature is able to overpower enthalpy, then the reaction will occur. So we say sometimes that in the last case there that high temperatures make the reaction spontaneous. On the other hand, the condition right above it, we would say that lower temperatures make the reaction spontaneous because in lower temperatures, enthalpy is able to overcome the entropy values. So these are the ways that chemists think about if a reaction is going to occur or not. And it all comes down in this context to delta H and delta S. But if the two of them are fighting, then you have to think about the temperature in order to see if the reaction is spontaneous or not. And remember, spontaneous means negative delta G. Those are the reactions which will occur. Non-spontaneous means positive delta G. Those are the reactions which are not likely to occur. A given reaction has a negative enthalpy and a negative entropy. What can be said about this reaction? Okay, so if it has a negative enthalpy, that's exothermic. And a negative enthalpy does contribute to making delta G negative. But if the entropy is negative, negative times that negative right there makes for a positive term. So entropy here does not want this reaction to go. So this reaction is not product favored at all temperatures because enthalpy and entropy have the same sign. If they have the same sign, then that means they're fighting, all right? And these have the same sign. They're not, one of them is not happy with this reaction. So it's not product favored at all temperatures. It's not product favored at any temperatures either. If you have them being opposite signs, that would be the case of A or D. So if they're both fighting, all right, you have to think about which one wants the reaction to be spontaneous, i.e., which one wants delta G to be negative. And delta H here wants the reaction to be negative. It's a negative delta H. So what we would say here is that if the temperature is lower, all right, then the lower temperature times delta S, which gives you, by the way, a positive number, it won't be larger than the negative delta H. Low and high here are very relative. It depends on the magnitudes of delta H and delta S. But at lower temperatures, delta H should be able to overpower delta S, making the reaction product favored and spontaneous. On the other hand, at higher temperatures, then negative T times negative delta S makes for a positive value. Positive values can overpower delta H if they get large enough, and you'd have a non-product favored reaction. To figure out delta G, all right, the way that people usually do it is delta G equals delta H minus T delta S, all right, and that's a great thing. They call that the Gibbs equation, by the way. But there are other ways to calculate delta G. One of them is if you have a table of Gibbs free energy values, and in that same table of thermodynamic values at the end of problem set number 5, there's a third column. One of the columns was for enthalpy, so enthalpy of products minus enthalpy of reactants. One of the columns was for entropy, entropy of products minus entropy of reactants. Well, the third column, guess what? Gibbs free energy values. Woohoo! And Gibbs free energy, if you have all of them, will equal Gibbs free energy of the products minus Gibbs free energy of the reactants. And probably if you have the values, this is the easier way to go. You can always do delta H minus T delta S, but you'd have to do delta H separately, delta S separately, and then in the third step, combine them. If you have all the delta G's, then man, delta G products minus delta G reactants, the way to go. Here are values of Gibbs free energy. And again, every table will be a little bit different. Gibbs free energy values are more like enthalpy values. They can be positive, they can be negative, and also they're equal to 0 for elements in their standard states. So this is very similar to the delta H values. If you look through those, the elements are always 0. Delta H values can be positive or negative. All of these are just numbers, though. You don't have to know any of them. You'll always be given the values on quizzes and exams and stuff like that. And again, like the other examples we've seen, if you take all the Gibbs free energies of the products and subtract all the Gibbs free energies of the reactants, you are good to go. Here's a reaction. We can calculate the delta G, the Gibbs free energy change for this reaction, diamond plus oxygen going to CO2. But notice here that I only gave you 2 values. I gave you diamond and CO2 only. Okay, for Gibbs free energy values as well as enthalpy, end elements in their standard states will have values of 0. So in this reaction, oxygen is an element in its standard state. It's going to have a delta G value equal to 0. It would also have a delta H value equal to 0. Elements in their standard states are 0 for both delta H and delta G. They are not 0, though, for delta S, or the S values. Entropy values are always positive, except for those perfect crystals at 0 Kelvin, which is like never. So always look up entropy, but the Gibbs free energy and delta H values here will be 0. So anyway, what you need to do is take the CO2 value and subtract the diamond from it. If you do that, you end up with negative 397.3 kilojoules per mole. Notice that diamond is not the natural state of carbon. The natural elemental state is usually graphite. So that's why you have a non-zero value there for delta G. Let's figure out the delta G of some other reactions. Let's combust carbon into carbon dioxide, so graphite plus oxygen making CO2. Products minus reactants, graphite and oxygen are both 0, like we talked about, negative 394.4 kilojoules. This says that forming CO2 is spontaneous. It's a negative delta G value. Carbon dioxide should form easily, and it absolutely does. Unfortunately for us, it forms too easy. This is the greenhouse gases kind of thing, causing global warming and all that kind of temperature changes and stuff. It forms actually very easy. Carbon dioxide does. So in this case, yes, it forms readily, negative delta G, for better or worse, as you can see. But anyway, that's neither here nor there. We can at least predict now if a reaction is going to occur or not. CO2 should absolutely form. Chemists talk about reactions as being enthalpy-driven and entropy-driven. An enthalpy-driven reaction is just a reaction where the enthalpy contributes to spontaneity. Now remember, spontaneity means negative delta G. And if you want a negative delta G, then you're going to ideally have a negative delta H. So an enthalpy-driven reaction is just a reaction that's exothermic. It has a negative delta H. An entropy-driven reaction means that your delta S value is positive. Positive delta S's contribute to negative delta G's as well. Some reactions are both enthalpy-driven and entropy-driven. Some reactions are enthalpy or entropy-driven, and some reactions aren't driven by either one. Just depends on the conditions. But looking at the sign of delta H and the sign of delta S, you can tell what's up.
When we pour sodium carbonate into hydrochloric acid, it dissolves rapidly to produce aqueous sodium chloride and gaseous carbon dioxide. In this case, entropy increases, and the reaction is energetically favored to occur. It is both enthalpy and entropy driven.
In this video, first of all, you saw something happened, all right? And just seeing something happens means that that reaction is spontaneous. So we would say the sign of that reaction, negative delta G, okay? In addition, lots of energy being given off. Things were bubbling. You would feel warm, I'm sure, if you felt the thing. That means it's an enthalpy-driven reaction, all right? Delta H is going to be negative. And finally, you saw all the bubbles form. Remember that entropy loves making gases. Gases have higher entropy than the things they come from. So this reaction is definitely entropy-driven. We saw the bubbles. Enthalpy-driven. Lots of energy release. That's what enthalpy is all about, exothermic. And finally, it's spontaneous because we saw something happened, all right? So this reaction has all the good things going for it. It's going to happen. Doesn't matter what conditions. This reaction's good to go. But not all reactions have favorable enthalpy and entropy values. We're going to look at that now here in a little bit. Let's look at the combustion of acetylene. Acetylene, which is used in torches a lot of times for welding and stuff like that. Acetylene is C2H2. It reacts with oxygen to make CO2 and water in a combustion reaction. I'm doing it here per mole of acetylene, so that's why the fraction is there. Fascist fractions. But anyway, we can use the enthalpies of formation to calculate the enthalpy of this reaction. So to get that negative 1238 number, and I encourage you to do it, you would take the enthalpy of the products and subtract the enthalpy of the reactants. So for this reaction, you take 2 times CO2 plus water, and all is gases, by the way, minus the enthalpy of C2H2, but you don't really need to calculate or find out the delta H of O2. Elements in their standard states are zero, so you don't have to worry about that. Anyway, if you do that, you should get a number, negative 1238 kilojoules per mole. This is a negative delta H, so that means this will be an enthalpy-driven reaction. You can do the same kind of process, but to find the entropy change, okay? Now, an entropy change, a delta S, would also be delta S of products minus delta S of reactants. And you have to look up everything on there. It would be 2 CO2s and a water minus the entropy of C2H2 and 5 halves O2. You do have to look up the entropy of O2 on this one because all elements and compounds have positive entropies as long as you're not at 0 Kelvin in that pure crystal. So if you do that, you should get negative 97.4 joules per Kelvin. Now, first of all, let's look at the sign. This is not an entropy-driven reaction. This reaction is not favored by entropy. And if you look at that reaction, you're going from 5 halves is 2.5 plus 1. You're going from 3.5 moles of gas to 3 moles of gas. So you're going from more disorder, more moles of gas, to less disorder, less moles of gas. Entropy's not happy with that. So entropy here is a negative number. Now, because delta H was in kilojoules, sometimes it's useful to turn your delta S into kilojoules as well, and that's what I did. You could also turn delta H into joules if you'd rather, doesn't matter. Anyway, delta G of the overall reaction, delta H minus T delta S, and let's assume that someone's welding at room temperature. There's the delta H, there's the delta S value. Delta G comes out to be negative 1209 kilojoules per mole. Negative delta G means the reaction's going to occur. It's spontaneous, it's product favored, all right? However, entropy is not happy with this reaction. Entropy doesn't want this reaction to occur. This reaction only occurs because enthalpy says, hey, I want this reaction to go. This reaction is enthalpy driven. So this is an example where enthalpy and entropy are fighting each other. Enthalpy is overpowering entropy at this temperature. The reaction comes out to be negative, spontaneous. Hey, go for it. Weld your stuff away. And that's good because everybody that welds wants to do welding, I would assume. They couldn't do that if that delta G value would have been a positive number. The dissolution of ammonium nitrate may not be the most exciting reaction to watch, but as we've seen earlier, adding ammonium nitrate as a solid to water, it does dissolve, okay? Because it dissolves, that means this reaction is spontaneous. Remember, if something happens, that means the reaction is spontaneous, but this reaction is endothermic. It takes energy out of the system, the temperature goes down. This reaction is not enthalpy driven. If you have an endothermic reaction, the reaction is not enthalpy driven. But because the reaction is spontaneous, i.e. it happens, you have to have the reaction be either enthalpy or entropy driven. It certainly is not enthalpy driven. This reaction must be entropy driven. Something has to be the driving force to make the reaction occur, all right? And it certainly isn't enthalpy here. So this must be an entropy-driven reaction. And let's check this out.
In the center beaker is water at room temperature. To this we add solid ammonium nitrate. The ammonium nitrate dissolves. Usually, a reaction that occurs so readily is exothermic, but we see from the thermometer that this reaction is endothermic. The temperature of the water drops significantly. This reaction is not favored energetically, yet it still occurs.
So we're seeing here again that this is endothermic, so this is not enthalpy driven, but the reaction occurs. You're seeing the solid dissolve. So it is spontaneous. A spontaneous reaction must be enthalpy or entropy driven. Entropy must be helping this reaction to occur. Let's calculate the actual dissolution of ammonium nitrate into a solution of ammonium nitrate. And if you look up these values in thermodynamic tables, all right, you'll find that the delta H, sure enough, is positive. And that's what we expected, all right? It's a positive endothermic number. We saw the temperature of the solution decrease. On the other hand, the entropy of this reaction positive, all right? Going from a very well-organized solid to a solution is usually a entropy-favored reaction. So the entropy here, positive 108.7 joules per Kelvin, or in kilojoules, positive 0.1087 kilojoules per Kelvin. So if you combine these two into the delta G reaction, sure enough, delta G, negative 6.7 kilojoules. Remember, negative delta Gs are the spontaneous reactions. Those are the ones that something happens. And sure enough, this stuff does dissolve, all right? Again, not as exciting as the other reactions necessarily, but if you see something happens, then delta G must be negative. And it wasn't happening because of enthalpy, that's for sure. Enthalpy doesn't want this reaction to go. This reaction is occurring because of entropy. This is an entropy-favored reaction. This is product favored. It's got a negative delta G. Remember, negative delta G means product favored, it means spontaneous, etc., etc. This reaction is entropy driven. Positive delta S's mean the reaction's entropy driven. Negative delta H's mean that it's enthalpy driven. This is not a negative delta H, this is positive delta H. Enthalpy doesn't want this reaction to go. It only happens because of entropy. Here's another reaction. This is an iron 3 oxide reacting with basically graphite to make pure iron and carbon dioxide. Well, if you look up these values for delta H and delta S or calculate them, there's what you get, and you plug it in at 298 Kelvin, delta G positive 300.8 kilojoules. So this reaction, because of the positive delta G, is reactant favored, non-spontaneous at 298 Kelvin. So initially, if you see a positive delta G, it might be kind of discouraging. If you really want to take iron 3 oxide and turn it back into iron, that would be kind of discouraging because positive delta Gs are the ones that don't usually happen. But if you look at this problem a little bit more carefully, the reason it's a positive delta G is because delta H is positive. Endothermic reactions generally don't occur. But delta S here is a positive number. This is an entropy-driven reaction. Now, at 298 Kelvin, the entropy is not able to overcome the enthalpy. But you can probably imagine, because delta G equals delta H minus T delta S, there must be some temperature at which temperature times delta S is able to overpower delta H and make the reaction spontaneous. The question here is, what temperature does it take to make delta G go from being positive to negative? What temperature allows entropy to overpower enthalpy and make the reaction spontaneous? This reaction will be spontaneous at higher temperatures. If delta S is positive and delta H is positive, then at some high temperature, negative T times delta S will be able to overpower delta H. So you can figure this temperature out. It's a threshold temperature because at the threshold, delta G equals 0. And if delta G equals 0, and remember delta G equals delta H minus T delta S, well, if delta G is 0, then delta H equals T delta S. And temperature then equals delta H divided by delta S. You have to make sure you're using the same kind of units like before. So I turned 560.3 into 0.5603 to make the kilojoules cancel out. But because delta S is kilojoules per Kelvin, you end up with Kelvin. Lo and behold, 835.1 Kelvin. Now, what that temperature means is that if you can do this reaction at a temperature higher than the threshold in this case, the reaction will be spontaneous. It will occur. So if you are really committed to turning iron 3 oxide, rust, back into iron, if you can get this temperature to occur at maybe 836 Kelvin, just a number a little bit higher than 835.1, you can actually make this reaction spontaneous, i.e. occur naturally. In industry, this might be something that's feasible, all right? You might be able to keep something warm enough to make this reaction go from being non-spontaneous to spontaneous. You'd have to get at pretty high temperatures, but again, if there's an economic incentive, maybe this is totally possible. This is the way, at least to calculate, when a reaction goes, in this case anyway, from being non-spontaneous to spontaneous. Here's another example. Ice going to liquid water at 273 Kelvin, that's the transition. All right, that's when liquid water freezes and solid water will melt. 0 degrees Celsius is the same as 273 Kelvin. Now, delta H is positive, all right? It takes energy to turn solid pieces into liquid water, all right? That's one of the things we talked about in Chem 222. You have to break the solid lattice, turning them into liquids and stuff to overpower the intermolecular forces, et cetera, et cetera. On the other hand, the delta S here is a positive. Liquids have higher entropy than solids do, so turning solids into liquids would have a positive delta S value. 0 Kelvin then is the threshold between when ice forms and liquid forms. Because delta S is positive, turning ice into liquid water, all right, if T delta S is larger, then it'll make negative delta G. On the other hand, if temperature is low enough, then delta H really isn't too into this because you've got to break the solid intermolecular forces in the hydrogen bonding ice molecules in order to form them liquid water. And that's that's going to take energy. So 273 Kelvin is the threshold between when this is going to happen naturally and when it won't. So ice won't normally go to liquid water below 273 Kelvin, but above 273 Kelvin, absolutely, ice cubes will melt easily. This is kind of a practical use of this threshold temperature, kind of an interesting idea. Here's a reaction. We've got a given reaction. It's not product favored at room temperature, so it would have a positive delta G. At what temperature will the reaction become product favored? And we have a positive delta H and a positive delta S. Okay, so this is like the example we did with the iron 3 oxide turning into iron, all right? We're trying to find that threshold temperature, and you can do that by letting delta G equal 0, and if it does equal 0, then delta H minus T delta S equals 0. Put negative T delta S on the other side. Delta H equals T delta S. T equals delta H divided by delta S. And remember, you have to get everything in the same kind of units. So I would turn the joules per mole Kelvin into kilojoules, but you could do it the other way around. It's like 50 divided by 0.1. 50 divided by 0.1 is 500. And it's in Kelvin because that's what the scientists use in thermodynamics all the time. At 500 Kelvin, that's the threshold temperature at which you go from being non-spontaneous to spontaneous, i.e. from positive delta G's to negative delta G's. So if you want this reaction to go, heat it up to like 501 Kelvin, something like that. In those kind of cases, you would have a spontaneous reaction. Delta G is related to K, equilibrium constants as well, all right? And delta G is the change of free energy when the reactants convert completely to products. Ks are greater than 1 when you're in product favored, so you can, if you have a large K, you can find the delta G. So both delta G and K are related to how favorable it is that the reaction occurs. And you can probably see now, K's larger than 1, product favored, delta G's less than 1 are the spontaneous reactions. So somehow we have to correlate a negative delta G with a K greater than 1, and conversely, a positive delta G with a K that's less than 1. So the equation that people use is delta G equals minus RT natural log of K. R here is the energy R. It's 8.3145 joules per mole Kelvin. Temperature is in Kelvin, and you can use any kind of K here to calculate a delta G. So it could be a Ka, a KSP, a KP. I mean, anything like that is fine. All of those can be related back to delta G and vice versa, delta G back to K. So this is another possibility that you can do in the world of thermodynamics. Here's an example. Dinitrogen tetraoxide breaking down to 2 nitrogen dioxides. The delta G positive 4.80 kilojoules. Well, let's calculate the equilibrium constant for this reaction. No problem. So 4.80 kilojoules, we're going to put up there for delta G. Usually R is just in joules, so let's convert the kilojoules into joules. If you have joules and kilojoules, you've got to have them be the same kind of unit, big time. But anyway, what I did, I took 4.80 kilojoules, turned it into 4,800 joules, multiplied by 1,000. That equals negative R, which has joules, times temperature, 298 Kelvin. We're assuming it's standard conditions, because that's what that little 0 thing right there means, natural log of K. So natural log of K equals, as it turns out, negative 1.94. If you need to get rid of the natural log, you use what's called the anti-natural log. We saw that for base 10 logs, log, you could go 10 to the x, that's the anti-base 10 log. Well, for natural logs, you use the little e to the x button. So usually on calculators, you'll have a natural log button, and then second function ln will be the little e to the x. That's the anti-natural log. K, if you figure it out, is going to be the anti-log, the e to the power of minus 1.94, and that equals 0.14. Please make sure you can do this in your calculator. In case you have to go from a delta G to a K, you'll need to use that anti-natural log, and so make sure you've got this process down. But what is really cool here, this was a non-spontaneous reaction, a positive delta G. N2O4 is not expected to break down to NO2 by itself. And notice K here, K is a number less than 1. That's a reactant-favored K, and that implies that N2O4 should be in a higher abundance than NO2. All Ks that are less than 1 are reactant-favored, so delta G and K should correlate really well, and that's a nice way to check yourself on these kind of problems. If delta G, again, is greater than 0, like it is here, then K should be less than 1. And likewise, if you had a spontaneous negative delta G, a delta G that was less than 0, your K value should be greater than 1, i.e. product favored. It's all coming together. At 452.2 Kelvin, an equilibrium constant for a reaction, 0.444, let's calculate delta G. Okay, before we do the math here, this K is less than 1. It's a reactant-favored K. And Ks that are less than 1 should have delta G values which are positive, non-spontaneous. So that's a nice way to kind of check yourself. But anyway, minus RT, natural log of K, is what you want to do. R 8.3145. T is the 452.2 value. Natural log of 0.444. Make sure you don't use the log log. You might end up, well, you will end up initially with a joule value, and notice that all of the answers there are in kilojoules. So make sure you turn your joules into kilojoules. This comes out to be answer A, positive 3.05 kilojoules. Answer D certainly does not make sense. A negative delta G would have a K value greater than 1. Our K here is less than 1. We should have a positive delta G value. Cool. That's it for chapter 16. I really appreciate you spending your time with me. This chapter really summarizes the rules that scientists use to decide if a reaction is going to happen or not, which is really cool. So there's a lot of powerful things in here. Definitely some ways to help you with this information. The study guide will be a bulleted list of some of the highlights from this chapter, and I do encourage you to go through it. I also encourage you to check out the concept guide. Lots of different problems in here. Some of this stuff from Chem 221, obviously, that we're seeing, in Chem 222 for that matter. The concept guide will have some worked examples of how these work out. Types of equilibrium constants might be helpful because we are talking about lots of types of equilibrium constants. Following this slide in the printed version, you can see the important equations from this section, and there's also some end of chapter problems with the answers that follow. And I encourage you to make sure you know how to do those, and if you don't, definitely reach out. And if you do reach out, definitely don't be worried about it. This is kind of crazy stuff. This is all material you can do, I promise. But at first it can be a little intimidating. So if you need to reach out for help, definitely reach out to me. You can also reach out to the Learning Success Center /Avid Center for help. They are also there to help you. You're going to get this stuff, I promise. So just be after it. Okay, good luck with your studying. Thanks for spending your time with me, and have a wonderful day.